Welcome to our discussion on significant digits. Well, if you've never heard of them before, you might be asking, what the heck is a significant digit? It basically just tells us, where we can round numbers and where we can't round numbers. And it's based on basically which digits in that number are considered significant information. So non-zero digits are always significant, right? So anything other than zero, we need to keep track of those. Zeros that follow a non-zero digit and lie to the right of the decimal place, as in 4.20 and 3.00, also always significant. Zeros between non-zero digits, as in the zeros between 4002 or the zero between 3.06, or other significant zeros such as the first zero in 30.0, those are always significant. Zeros to the left of the first non-zero digit. So if you have a really small decimal that starts with a bunch of zeros, so 0.006 or 0.00052 and et cetera, those are never significant. And zeros to the right of the last non-zero digit, but before the decimal point, as in 40,000, 210, right, 1 million, things like that, they're not significant unless stated otherwise. And basically this all comes down to how we can take numbers and kind of convert them into scientific notation. So let's state the number of significant digits and the implied meaning of the following numbers. So you have a time of 11.90 seconds, a length of 0.000067 meters, a weight of 0.0030 grams, a population reported as 240,000, or a population reported as 2.4 times 10 to the fifth. All right, so let's look at them a couple at a time. So 11.90 has 4 significant digits. And the reason why that last zero is important is because it tells us that that's how accurate the measurement is, right? It implies a measurement to the nearest 0.01 or 100th of a second. So for this length of a meter, it only has 2 significant digits because all of those zeros before the decimal place don't tell us anything. It implies a measurement to the nearest 0.00000, right, 1 meter, right? But you can always rewrite that in a smaller measurement. So in the case of this, it would be 67 micrometers, because that's the nice thing about oh gosh, I'm completely blanking on the name of it, the metric system. All right, some more examples, right? For the same reason as the other ones, these two zeros are insignificant. So the 3 and the 0 at the end, those are your significant ones because it tells you how precise the measurement is. And just like with the other, you can rewrite this, right? Instead of in grams, you could make it 3.0 milligrams. And again, this 0 would be significant because it's telling you how accurate the measurement is. All right, 240,000, of course, those zeros are insignificant, right? Because you can just think of 24 and then, it's a 10,000th. It's basically implying that you've rounded, because I doubt a population is exactly 240,000, right? They've obviously rounded to the nearest 10,000. And then this one has 3 significant digits. Even though it means the same thing as the other number, the scientific notation shows that the first 0 is significant, so it implies the measurement is accurate to the nearest 1,000 people. So it's interesting how that happens, but that's just what we assume when we see scientific notation. So if we were really going to represent 240,000 as a scientific notation, we would not include that extra 0. You would just put 2.4. Okay, so rounding with significant digits. Let's see if we can round each thing So 7.7 times 9.92, give your answer with 2 significant digits, and so on and so forth. Okay, so 7.7 times 9.92 equals this. Because we're asked to give the answer with 2 significant digits, we would round to just 76 square millimeters. When you do this multiplication, give your answer with 4 significant digits. You do all the work, which gets you this big, huge number. And because we're asked to give the answer with 4 significant digits, it would just be 1.73, and then that fourth one, that 0 would round up to a 1. Now you'll notice that when we're rounding, we don't round each thing first and then do the work. You do the multiplication and then round your answer. Okay, random errors occur because of random and inherently unpredictable events in the measurement process. A systematic event, or systematic error, occurs when there's a problem in the measurement system that affects all measurements in the same direction, i.e. everything gets over-measured or under-measured, right? So everything comes out too high or too low. That's a systematic error. The absolute error describes how far a value is away from its true value, right? So it's basically just the measured value minus the true value, and that gives you its difference. And then the relative error is just that difference divided by the true value. So we've seen this absolute versus relative before with percentages, right? Relative always just means divided by some sort of reference value. And in this case, the reference value is the true measurement or the true value. So let's find the absolute and relative error. A projected budget surplus of 17 billion turns out to be 25 billion at the end of the fiscal year. So when you do the subtraction, that's 8 billion over. And when you do 8 billion over 17 billion, that tells you were 47% over, right? So anytime, remember we talked about relative always means percentages. So anytime you do a relative, your answer is always going to be a percent, because it's basically giving you what percent of that bottom number, right? What percent of that reference number are we talking? So accuracy describes just how closely a measurement approximates a true value. So an accurate measurement has a very small relative error. Remember, relative error is the absolute difference between the measurement and the actual value. And then precision describes the amount of detail in a measurement. So that tells you like to how many decimal places your measurement goes. That's your precision. Accuracy is how close you are to the truth, and precision is basically how many decimal places you have. So the rounding rule for addition or subtraction: round the answer to the same precision as the least precise number in the problem. Right? So if you're adding a whole number with something that has 1 decimal, then your answer should have 1 decimal. If you're adding or subtracting a number that has 1 decimal with another number that has 2 decimals, then your answer should have 1 decimal. I'm sorry, I misspoke on that first example. If you're adding an integer to something with 1 decimal, your answer would just be an integer, the least precise of the two. And then rounding rule for multiplication or division: round the answer to the same number of significant digits as the measurement with the fewest significant digits. So it's the same rule, basically. It's just described 2 different ways. So in both of these things, you're basically rounding to the least precise, or the one with the fewest significant digits, which is the same thing as the least precise. So a book written in 1985 states that the oldest Mayan ruins are 2,000 years old. How old are they now? Well, the book written in 85 is roughly 30 years old. That is, of course, if this was 2015, but since it's 2020, when I'm recording this, that would be 35 years old. So you'd add 35 to it instead of 30. But however, 2,000 years is the less precise of the two numbers. So it's only precise the nearest 1,000. So whether your answer was 2030 or 2035, you would still round back to the nearest 1,000, and you would still say it's roughly 2,000 years old. So that's the idea of this number is precise only to the 1,000. This is precise to the 10th place. When you get this, you would round it back to the 1,000th, and you would get that it's still roughly 2,000 years old. So that's the idea of precision, is because we don't know how precise this number was. It was only precise to the thousandth. So our answer is rounded back to that. Our last example, the government in a town of 82,000 people plans to spend 41.5 million this year. Assuming all this money must come from taxes, what average amount must the city collect from each resident? So to find the average tax, we're going to take that 41.5 million, which has 3 significant digits, right? And we're going to divide that by the population of 82,000, which has 2 significant digits. So the population has the smallest, right, 2 significant digits. So the answer should be rounded to 2 significant digits as well. So we're going to take 41.5 million, which is this big old number here. We're going to divide it by 82,000. We're going to get this, and we're going to want to round this to 2 significant digits, right? So the second significant digit would be the tens place, and we would round it to approximately $510 per person. Okay, that's everything on significant digits.